velocity here for the last one.
It's a lag, right?
That's a lag compensator. Yeah, we'll go with that now. Any question about the lead compensator, the two methods?
Have you started with that?
What's the advantage of method one?
No, Mark. Yeah. Okay.
Because one of them is so easy.
I gotta start
One of
on
the
it.
methods is just basically you cancel out the zero and pole and then it becomes so easy.
Yeah.
Why would you use the other one?
That other one results in a generally a smaller steady state ramp error. Steady state. If you apply a ramp type signal, then the error, the response will have a smaller error than what you would get using that's a 2. Okay. So that's one advantage. They mention that there in the book about that.
One more thing, can we use any other method in the test?
Sorry?
Can we find the poles and zeros of the compensator using any other method, any technique?
I probably will specify the method.
Oh,
Okay, so you should know both methods.
right.
So I'll start out with this lag compensation, and I'll show several graphs. We'd like to plot step response, ramp responses. But for lag, compensation, we have the general closed loop control system. Looks like this. We have the GC of S. That's our lag compensator, and it will have this form here. It is case C hat times S plus 1 over T divided by S plus 1 over beta T. So that's the compensator there. And then we have the plant G of S. And it has a general form, say, K P of S over S to the N times Q of S. And let's say we have unity feedback. And so, yeah, as far as the lag compensator is concerned, this beta here, beta is greater than 1. Okay, and what that means is that this pole will lie to the right of the 0 for the compensator. It's just the opposite from the lead compensator. So if you put down the poles and the pole and 0 of the compensator, so we'll have a pole here and a 0 here. And as you'll see in the design of the lag compensator, the poles and zeros are put close together. The pole and 0 are put close together, and they are also put close to the origin, so that we can get satisfy the steady state accuracy specification. So that's the purpose of the lag compensator, is to satisfy a steady state accuracy specification. In other words, in response to a step or a ramp type of input, you like to get a certain small error between the commanded input and the output response in the steady state. So with the lag compensator, we would be satisfied with the transient response, but we're interested in improving the steady state response, right? So there's two portions of the response: the transient response and the steady state response, okay, having to do with the state, with accuracy in the steady state. So with this lag compensator, the root locus should not change much in the region of the dominant pole of the forward path transfer function. Okay, in other words, with this equal to 1, we would have, we could draw the root locus, and I'll show you that in just a little bit. We could draw the root locus plot based on this G of S here, and take a look when the gain K is just equal to 1. Okay, and take a look at the pole, closed loop pole, and then insert the compensator here, whose purpose is to increase the accuracy without, affecting very much the transient response. Okay, so what that means is that the root locus in the region of the dominant pole will look much the same as that of the open loop transfer function, as that of the system with only the G of S in the forward path. Okay, so what I'd like to do is kind of work backwards. In other words, I'll start and show you the solution, the final design of the lag compensator, and how it does provide an increased steady state accuracy in response, in the example, to a ramp input. Okay, so let's see. I think I'll try to stay in this region here so that I can bring down the screen in a little bit. And
do you mind writing in black? It's a little hard to see.
You want
but
black?
I can give you more.
I do have black. I can try to use blue, but the reason I was using red was that it erased more easily. And maybe blue does the same thing. Maybe blue will work. I'll try that. But I tried the black a few times and it was hard to erase. Okay, so here, let's consider, it's the example that they go through in the book. And it is, you've got this, and you've got compensation K equal to 1, which is essentially no compensation at all. Okay, and then you have the plant, which is 1.06, that's given, divided by S plus 1, and S plus 2. Okay, and then we have unity feedback. Okay, and so what we're saying is that this closed loop system has a satisfactory transient response. A satisfactory transient response. Okay, it's before it goes into steady state. So we're satisfied with that, but we're not satisfied with the accuracy that this system yields in response to a ramp input. Okay, so let's take a look at the steady state ramp error. E steady state for a ramp, is equal to 1 over kV, and you recall, I might call that kV prime here, because that's the static velocity error constant for the uncompensated system. For the compensated system, I'll call that K sub V. Okay, so this kV prime is equal to, remember, is the limit as S goes to 0 of S G of S. So you multiply by S, that cancels that S in the denominator, and then when you take the limit as S goes to 0, this becomes 1.06 divided by 2 equals 0.53. 0.53. And so the steady state ramp error will be 1 over that. So 0 K sub V prime is equal to is equal to 1.8, about 1.8. Okay. And so what that means is that if you apply a ramp which has a slope of one, so it's a unit ramp, what they call a unit ramp, right? You'll get a response. There is a transient, and then it goes into steady state. And so at some point after it has gone into steady state, say here, we can determine that this is the error in here, 1.8. Okay, and so what we're saying is that this is too large, right? And what we would like, right? The objective is to decrease the steady-state ramp error by a factor of about 10, right? So what we would like to do is decrease this to about 0.2, right? Or 0.18, which is about 0.2. Okay. So due to a decrease in this E steady state ramp by a factor of 10. Okay. So now let me give you the design, the final lag compensator design, and show you how it has in fact decreased it by a factor of 10, and then we'll get into the design. Okay. Actually, what we'll do is we'll take a look at those the locus plot and the ramp response. Okay, so E steady state ramp for the system, the lag compensated feedback control system. For the lag compensated feedback control system, with the design, the GC of S turns out to be 0.97 times S plus 0.05 S plus 0.005. That's a compensator, and then we have the plant in there. So the plant is the same, and so we have the 1.06 divided by S plus 1 and S plus 2. And so and so here let's find the steady state ramp error for this design here. So E steady state ramp error is equal to, again, 1 over case of V. Now this time we're calling it case of V instead of KV prime. The KV, you recall, it is just going to be equal to the limit S goes to 0. We have to now include the GC in along with the GP, so the GC, it's actually S times, right? Just like up here we had S times. GC, GP, well, it's not GP, it's just G. Okay, and so that then is going to be equal to, let me see, the KV is going to be equal to the limit as S goes to 0 of 1.02, 1.06 times 0.97, and 1.02 roughly times S plus 0.05, right, divided by S plus 0.005. You know, we're just substituting there. We have S plus 1 and S plus 2. And so this could also be written if we put it in what's called like a time constant form. In other words, each of these factors is 1 plus a factor times S, a constant times S. then we could put this into this form of the limit s goes to 0 of 0.05 times 1.02 divided by 0.005 times 2. Okay, and this number turns out to be 5.12. And then what we have, oh, I didn't finish. And so what we have there is that times the 20s plus 1, that's in the numerator. In other words, I factored that 0.05 out, right? And so I have 20 times s plus 1. And divide, and then we're dividing by s and 200 s plus 1, and then s plus 1. I factor that same thing, and then we have 0.5 s plus 1. Okay, and so you're taking the limit as s goes to 0, and so all of these are go to 1. These all go to 1, right? Because it's s goes to 0 there, and all the way across. So this is just 1, and this is 5.12. Okay, so it's equal to 5.12. Compare it with what we had up here is 0.53. So you see that it is in fact a factor of just about 10. Difference between if you multiply, if you divide that by 10, right, you get 0.51, which is close to 0.53. Okay. So now let's find the ramp error. The ramp error is just a reciprocal of that. So the ramp error is going to be 1 over 5.12. It's going to be equal to 0.2. 0.2 as opposed to 1.8. So it has significantly reduced the steady state ramp error. Okay. So now let me show the plots here and the root locus.
Quick question, why do you use constant 0.87? I mean, the root of 0.05, for any reason?
You're saying where does this come from?
Yeah.
That's what I'm going to show. In other words, I started at the end with a design, and I showed that this design did in fact decrease the ramp error by a factor of 10. Okay, and yeah, so that's what I want to show how to get this, and that. Okay. So I was, try something, do it a little differently. Start at the end. And so anyway, this is the code here. Maybe interested in that, I will post it. So I define the system, the original system, open loop transfer function in terms of the ZPK command, and you see the 1.06, and then I do the root locus for it, and then I form the closed loop system. But it's for the original system there, right? Original system, and I look at the step response of the closed loop system, and then I take a look and look at the ramp response. The ramp response, the way to get the ramp response is to get the step response of the system with an s in the denominator, right? Because a ramp Laplace transform is 1 over s. The step Laplace transform. Sorry, the ramp is 1 over s squared. the plug. The step is 1 over S. So you put an extra S, and as the book explains, you can find the ramp response using the step command. Okay, and that's what it is here. Use a step command based on this modification of the denominator. It's a 152. It's a closed loop, and so and this one is for the lag compensator. I put in the pole and the zero, right? For zero, that's a pole and that's a zero. Yeah. and so I'm using the ZPK command. Do the root locus on that. I did a few other things on there. I look at I use a subplot to depict the root locus plots of each, and side by side. In other words, in a 1 by 2 picture. And so I have them here. I think I'll just use them as I have them. And here, this is the original. This is the root locus of the uncompensated system. In other words, with this k equal to 1. Actually, this root locus, the k goes from 0 to infinity, so I have to pinpoint where k equals 1. Okay, so this k equal to 1, and where is that here? 0.95. Anyway, close enough. Your closed loop transfer function pole of the uncompensated system, right, with the gain k essentially equal to 1, you have a damping ratio of 0.49 or 0.5. Okay, and you have the closed loop transfer function poles at minus 0.33 plus and minus j 0.57. Okay, and also this gives you the overshoot in response to a step input. Now this system here is a type 0, type 1 control system. Therefore, the steady state step error is going to be 0, right, for a type 1 control system. So to have that. So what we want to do is maintain that dominant pole location there. But what we need to do is increase the steady state accuracy. Okay, and so now let me show the step response briefly. The step response is here, and notice that it has an overshoot of about 16%, right? And so what we're saying is that actually we are interested in the ramp response, right? We want to have 0. We want the ramp error to be 0.2. Okay, we want it to be 0.2. But for this uncompensated system, the I have it here. What you can see is that after it has gone into a steady state, it's basically in a steady state. Right? This is a straight line. You see that at 12 seconds, it should be 12 because the input ramp is a unit ramp, right? The slope is 1. So, but it's actually, the amplitude is 10.3, so the difference is 1.7, right? And that's what we're saying. I have 1.8 here. So that is the steady state ramp error, right? And we'd like to decrease it. And so actually, this is the root locus of the lag compensated system. And we can take a look at the, you know, yeah, well, let me take a look at both of them together. I have both of them together here. So the left one here is for the uncompensated system, and the right one is for the lag compensated system. So you see those, the compensator 0 and pole are very close to the origin, right? 0.05 and 0.005, right? The poles are there at 0.005. And so it's practically at the origin itself. And this one is also quite close. So that it's all, you know, it's shown here. So, I mean, what you have is, you know, we could draw it briefly here. We do have a pole to origin. That's the plan here. And then we have the pole of the compensator very close to it, like that, say, and then the 0 over here. Okay, so, and then we have the other pole, 2 poles at -1, say, which is out here, so -1, and -2 over there. And so if you wanted to draw the root locus plot, right? Yeah, the root locus exists here, it exists here, right? And it exists over here. And so what this is going to do, it's going to break away, and it might go along towards some asymptotes. But in fact, what it does is you can see where I kind of enlarge that region about the origin. Is what it does is you know, it breaks away, then it re-enters, and one goes towards that finite 0, and the other one comes this way, and they here's a 0, and -1. Let's see. And so this, you see, it just goes out to -0.5. From this is the origin there. It goes up to -0.5. -0.5 is here, and so it's going to one is coming around like this, the other one's coming around like this. One goes that way, another one goes that way, and then it breaks away. One goes up like that, one goes down like that. So you can see that there will be some asymptotes involved, and you can find the angles of the asymptotes if you needed to. Okay, so and so let's go back to the the one where the 2 are together. Remember this one here, and notice that when the gain decay is set to about 1. That's close enough. And here the gain would be set to well, actually the gain would be set to 1.02, and so you've got increase that a little bit. Right about there, can't get it very well, 1.02. And so now you can compare the closed loop pole here, -0.3 plus J.58, and here it's -0.3 plus J.57. So they're very close to each other, right? So this, it has maintained fairly closely the desired dominant poles. Okay, the dominant poles closed loop system dominant poles have been maintained, which means that you'll get the kind of transient response that you wanted in the original. So with that then, let's go into the procedure for the design.
Yeah, so this is a way to reduce the steady state error. How will we go about reducing the transient response?
To improve the transient response?
Yeah.
With lead compensation. Yeah, lead compensation improve the transient response. Lag compensation improve the steady state response. And they have a section in there on lead lag where you do both of them together. I'm just going to do lead and lag separately.
As far as percent overshoot, is there a way to, does it matter as much for percent overshoot? Because it seems as though when you do the lag compensator, you're increasing the overshoot.
In fact, that's true. The overshoot increases with lag compensation. It went from 16 to 19 or so % overshoot. And so if you can tolerate that, that's still acceptable. And if it's still within your specifications, then it's okay. In other words, the overshoot you might have a range, maybe between 15 and 20. So in this case.
So, just so if my understanding is correct, if we were to do a lead compensator, that would reduce the overshoot.
The lead compensator would reduce the overshoot. In other words, you specify, for example, a damping ratio and an undamped natural frequency for the dominant pole. So the dominant pole basically dominates the response, okay? And so the damping ratio controls the overshoot, right? The peak overshoot. Okay, so yeah, so I'll raise this thing, and so you see basically you have the final design over there, and you see the splits. I didn't plot the ramp response of the lag compensated system, but here you can see what improvement you would get. 0.2. The book does give you a plot of the ramp response. In the lag compensation, what we said, this satisfies a steady state, a static error constant, which means it satisfies a certain steady state step or ramp response. Okay, and so that's what we would be given, right? That's a certain steady state error, or equivalently the static error constant, the Kv or the Kp. Okay, so we're given that, and the compensator transfer function, right? The general form we wrote down over there, where so here we have the GC of S is equal to the K at so the K at C times S plus 1 over T S plus 1 over beta times cap T, and so beta for the lag compensator is greater than 1, because the pole is to the right of the zero. Okay, so we have that, and so the lag compensator design is not unique. There are several possible lag compensator pole zero choices. The pole zero choices, in other words, the choice of that cap T, it gives you the zero. And then the choice of beta gives you the pole. Okay. And it turns out that, like I was saying earlier, the pole and zero of the compensator are placed very close together, right? This zero and that pole, they're very close together, right? And also close to the origin, because they will, doing so will minimally affect the desired, or the dominant pole locations, the desired dominant pole locations, right? In other words, I can make this drawing here. We have the pole, which is minus 1 over beta t, and the zero of the compensator at minus 1 over t, right? And we have our the dominant pole here, desired dominant pole of the closed loop system, right? Here called S1, okay? It has some real imaginary components to it, right? And so we can draw a vector from each of these, the zero and the pole here, and we have this angle here. So we have this angle theta sub z for the zero, and this one is theta sub p. And notice that theta sub z is less than theta sub p. Okay, and so if you take the difference theta z minus theta p, it will be less than 0. Whereas for the lead compensator, we had, of course, just the opposite, right? The 0 was to the right of the pole, and this difference was positive for the lead compensator. And as a result of these being very close together, what you see is that if you take the ratio of the S plus 1 over beta t, you take the magnitude of the magnitude of the ratio. What do you think that you would get? And keeping in mind that these are close together and also close to the origin, if they're very close together, you can see that these two vectors are very about the same length, right? About the same length, and therefore this ratio will be approximately equal to 1, right? Approximately equal to 1. So you can see that if you have the case of C, the case of C hat, and there, C hat, this would be approximately case of C hat. Okay. Okay. So the negative phase, right? We have negative phase. It has to be quite small so that the dominant poles are not significantly affected, right? And therefore, the author specifies a range for this difference here. He says that theta z minus theta p, the phase of, in other words, right, like the phase. Well, actually, it is a phase, right? It is a phase, and so should be greater than -5. It is negative, right? So it should be greater than -5 and less than 0. In other words, it should be on this range, on this range as far as the difference, theta z minus theta p, if this is 0 and this is -5. It should be on that range in there. So, or you could equivalently write that instead of this, you could just write the phase of s plus 1 over t divided by s plus 1 over beta t, over beta t, t. When evaluated at that point S1, S1 should be greater than -5 and less than 0. Right, so I could put here, like when evaluated for S equal to S1. This are dominant pole locations there. Okay. So now, as far as how do we choose the T here? There really is so many choices for this cap T. We know we wanted the 0 to be close to the origin. So, what you do is arbitrarily select the value of T that is quite large, right? Because you want the ratio 1 over T to be quite small. In other words, you like the 0 to be close to the origin, right? Both the pole and 0 close to the origin. Okay, so based on that and that alone, he said, all right, let T equal to 20. Right? Let T equals 20. And right, so that's where the 0.05 comes from. But now let's take a look at the case of V. The case of V. Case of V is the lag compensated static velocity error constant. Okay, and you know that it's equal to the limit as s goes to 0 of s times gc of s times g of s. Right. And see, what is it equal to? Limit s. So we have
beta by g,
so the limit is equal to
we can
yeah,
see
see,
beta k.
we're going to use this KB prime over here. We use this KB prime. That's the limit of S G of S, and so yeah, when in other words, when you let S go to 0 here, you get the KB prime there, okay, and here this S, again, we'll cancel with that S in the denominator there, and the GC there just becomes KV, what, a KV, a KC, right, it's this KC here, KC hat times what?
Beta.
Beta times KV prime, okay? And we know that this case of C is approximately, let me see what do here. If this case of C is equal to is equal to 1, right, then this ratio would be equal to 1, right? And so this is going to be equal to 1, and that's approximately equal to 1, okay? Approximately equal to 1. We'll find the more correct or accurate value by using the magnitude condition. And now, see this right here, this product here, what should this beta be chosen as if we want the case of B to be equal to 10 times what it is there, right? We want it to be 5.12, and so what should we choose beta to be equal to about? Choose beta equal to 10, okay? So we choose beta equal to 10, right? And in other words, this beta kv prime to be equal to the desired kv. And in the specific case here, the beta times the kv prime, the kv. We know that this is equal to roughly 0.5. Okay, and we want it to be a factor of 10 larger, so we want it to be equal to 5. So you can see that beta has to be equal to 10, roughly 10. Okay, so we've got the design actually practically, right? Because we said we'll set t for 20, our beta has to be equal to 10. And so here we have the 0, we know the 0 in the pole, okay? What's left is to find this Kc hat, which we know is close to 1, okay? But you can apply the magnitude condition to find a more precise value. Now, you also have to satisfy this specification here. And you can, right? In other words, since you know t and you know beta, you can, in fact, do the computations to determine that this is satisfied. If it's not satisfied, then you have to go back and choose a different value of t. Okay? So, and this one here, the reason for this is that we don't want a large negative phase contribution from the lag compensator, because it would cause the desired dominant closed loop transfer function pole to move away from what you really want. Right? So you tolerate a little bit of negative phase from the lag compensator. Yeah.
Just as far as a negative fact is concerned, is that a kind of arbitrary value, or is that chosen for some specific reason?
I think it's just chosen to be small. So I mean, you could design it such that it's even smaller, but if it's too large, then the closed loop, the desired closed loop dominant pole will deviate from what you want it to be. Does that sound reasonable?
Yes.
Okay. So, yeah. So the last thing is to find the Kc hat here. So what we have is this for our open loop compensator. We have the open loop transfer function. The open loop transfer function, in other words, the GC of S times the G of S is equal to the Kc hat. That's what we're trying to find. And here is the design: S plus 0.05, S plus 0.005. Right? That's what the pole would have to be is 1/10 of this pole here, of this zero here. Okay. And then we have the 1.06 divided by the S plus 1 and the S plus 2. Okay. So this is the open loop transfer function, and we know the characteristic equation is 1 plus this GCG, that's enough, is equal to 0. The H is equal to 1, right? So this is the characteristic equation, and this, it has this case of C hat in it, and you know that the magnitude condition is that you just set this equal to -1. Set that equal to -1, and then you can solve for K sub C, right? And so K sub C hat is going to be equal to the S plus 0.005 times the S plus 1 and the S plus 2 divided by 1.06 times the S plus 0.05. And then this would be evaluated at the desired pole, desired dominant pole, which, if you recall what it was minus 0.33 plus or minus J 0.58. Okay, that was the original desired closed loop transfer function pole, dominant pole. I say dominant because there are a couple of other closed loop transfer function poles. Actually, there would be 4 closed loop transfer function poles, right? Because the order of the open loop transfer function is 4, so the closed loop transfer function order is also 4, and so there would be 4 closed loop transfer function poles. But the main one, remember the root locus, what it looked like was a pole at the origin, another pole, and a 0 for the compensator, right compensator, and then we had another pole out here at -1, and another one out here at -2. Okay, and so what we saw was that this looks like this. And it comes this way, and then one goes off in this direction, the other one goes off in that direction, and it's right in this region here that we have our dominant pole. Okay, and the other poles, we would have. What did we say? That it looks like this and like this. That this one goes like that away from that pole, and this one like that. Okay. So there's going to be, there will be two poles in this region, 2 closed loop poles in this region, 2 more here, and 1 out here. Okay. So I know this root locus plot looks strange compared to what you've seen. The ones I'm not necessarily going to ask anything that complex, say, as far as test question, you know. But, still you have to have good command of, the root locus construction rules. You know, from here, we can find the case of C hat. It turns out then therefore to be 0.97. By substituting in this desired closed loop transfer function goal. So, you know, actually there's a lot of explanation, but as far as the design is concerned, it's pretty simple. Okay, it's kind of started out here where you have, actually it started out here where you have the steady state ramp error is larger than what you want. Okay, and this is the static velocity error constant for the uncompensated system. So for uncompensated system gives you that. We need to make it better. We need to make it the reciprocal of this, right? 0.2, that error, 0.2. So it's a factor of 10 better, roughly, right? If you divide that by 10, you get 0.18. So it's a factor of 10 improvement. So we have our case of B prime. We know that this in here, the compensated design, we choose T to be quite small, right? Very close to the pole, T very large, so that the zero will be quite small, okay? Close to the origin, and 1 over beta T with beta greater than 1 will be even smaller, right? In this case, a factor of 10 smaller. Okay, so if this is 0.05, then that's 0.005, right? And so we chose that T rather arbitrarily, but the author chose it as 20, but we have to maintain a rather small phase error, negative phase contribution due from the lag compensator, and it has to be on this range here. Right, this S1 here, this S1 is that same 0.33 plus or minus J 0.58. That's this.
How did we arbitrarily choose that point?
Sorry.
I'm just a little confused on how we are. Did we just arbitrarily choose that point, or?
But at this point, no, it's not arbitrarily chosen. It is the original root locus for this system here. Looks like this. We have a pole at the origin. We have a pole at -1 and a pole at -2. Okay, this root locus exists here and here. It goes away. It breaks somewhere here, and it goes into the right-hand plane eventually. And so, with the gain k equal to 1, see that this is with unspecified gain k. This is unspecified gain k. K equals 0 here, k equals 0 here, k equals 0 here, and as k increases, we plot the movement or the migration of the closed loop transfer function poles. And when that gain k is equal to 1, we get this S1. Okay. We got that S1 there. That S1 is this. Right. That's what I showed, if you can recall, from the plot, the Lewis plot, MATLAB. Okay. So, and you want to maintain that at that position. Okay. And it turned out that this is the design with the product here. Actually, this is not 0.97, right? This should be the product of this and this. The product of 0.97 and 1.06. Right? So this is 1.02 roughly. That's what I have. 1.02, right here.
Oh.
So that's the final open loop transfer function.
Okay.
Yeah.
Got it, got that.
Thank you.
So that homework problem, I think, is very similar to this.
Yeah, they give you, KV.
They gave a KV. Yeah, so that's the KV prime that I'm using here. Oh, no, wait. It gave you a KV, so that's a desired KV. Okay, so you
And they
can
give you
find,
a pole,
sorry,
and they give you the pole,
the pole for what?
the S1.
Oh, it gave the desired pole, oh, okay. So it should be fairly straightforward. Let's see. Any other questions, comments? Can't think of anything else. I think I made it to a Thursday. So what we'll start talking about, we'll go to, I may consider one other section here. I'm not gonna do the combination lag lead. I may consider, what's called, velocity feedback. And then anyway, after that, I'll go into the next chapter, which I think is chapter 7. In chapter 7, what we're going to start on is Bode diagrams and Nyquist diagrams, and then we'll get into the design using the frequency response. Okay, here this is a root locus design. Design of compensators using root locus. There is design of compensators using the frequency response, basically using the Bode diagram, okay, for design of lead and lag compensators. And that would, when we get that done, that'll be pretty much it. I'm not going to go into chapter 8, but I think we have a fair amount of stuff to, do between now. It's one more month,
Can you assign me a project?
So there's no project.
No project?
Just,
Can you assign one?
oh, can I assign one?
Just for fun.
Oh,
Not like, not graded, something to just do,
oh, yeah. Let me look at something.
like optional.
Yeah, I don't have anything off the top of my head. I'll look at something.
Cool.
Okay.
As far as designing with the Bode and Nyquist, what are the advantages to using those techniques as opposed to this?
Sorry, what?
Designing with Bode and Nyquist, what's the advantage to building the control loop system through that technique?
Well, it's just another technique in your repertoire. I think it probably is a little easier using root locus because you can associate the time domain specifications, like the damping ratio and indent natural feed to a certain point in the test plane.
I didn't sign
So root locus, what you would be given is, you have to be able to relate, for example, the damping ratio to the related to already related to a 7% overshoot. But I think that generally the time specifications are often given in terms of time domain specifications. So you have to convert time domain specifications to frequency domain. So in that sense, it may be more not quite as straightforward in designing compensators using the frequency response as using the root locus. Well, I guess that'll be it for today.